In this problem, a structural member that is 2 meters long is found to be 1.5 millimeters short when positioned in a framework. To enable the member to be fitted, it is heated uniformly along its length, given a modulus of elasticity equal to 200 gigapascals and a coefficient of thermal expansion that is equal to 0.000012 per degree Celsius. We are tasked to compute the temperature rise to enable the member to be fitted, and compute the strain of the member, and to compute the residual stress in the member when it cools down to its original temperature. Now for the first problem, the change in length due to thermal expansion is given by delta L equal to the coefficient of thermal expansion multiplied by the original length times the change in temperature. Rearranging to solve for delta D, we have delta L all over the coefficient of thermal expansion times the original length. So plugging in the known values, we have delta T equal to 1.5 millimeters, that is the change in length, all over the coefficient of thermal expansion, that is 0.000012 per degree Celsius. Multiply this by the original length, that is 2 meters or 2000 millimeters. We get our final answer, that is delta T equal to 1.5 over 0.000012 times 2000. We have delta T equal to 62.5 degrees Celsius. That's the final answer for the first problem. And for the second problem, we are tasked to compute the strain of the member. That is, using the formula, the strain is defined as the ratio of the change in length of the member to its original length. We can substitute the known values. We have 1.5 millimeters change in length all over the original length, that is 2 meters or 2000 millimeters. We can cancel units, so we have strain, that is a dimensionless quantity having a value of 1.5 divided by 2000, that is equal to 0.00075. That is the answer to the second problem. And for the third problem, the residual stress in the member when it cools down to its original temperature. When the member cools back to its original temperature, the contraction due to the thermal strain will induce a residual stress. And to compute this stress, it is calculated by using the formula for modulus of elasticity, that is equal to stress divided by strain. Rearranging, we get stress is equal to the modulus of elasticity multiplied by the strain. So we can compute for the residual stress, that is equal to 200 gigapascal or megapascals, which is dimensionally equivalent to Newton per millimeter squared, multiplied by the strain, which we solved earlier, that is 0.00075. We get our residual stress, that is equal to 200,000 times the strain. We get 150 Newton per millimeter squared or megapascals. And that is our answer to the third problem.